Um, in this morning's lecture, I told you a lot about the properties of QCD. And essentially, I finished the aspects of QCD formalism that we need to understand what events actually look like at the LHC. So now in this lecture, we're going to do a more, I guess, heuristic and phenomenological discussion of what is actually seen at the LHC and how some of the experiments are done. So probably the first thing to do is to look at the LHC detectors. The LHC, actually, both the LHC detectors and the LHC accelerator are really fascinating technologically. There's no time to discuss that in these lectures, but I gave you in the introduction references to the J-Inst articles about the LHC detectors and the LHC accelerator. And I really, these are very substantial articles of several hundred pages each, but it's worth your time to go through those and see really what it takes to do a modern particle physics experiment. The LHC is a ring which is 27 kilometers in circumference, and around this ring there are, I think located roughly here, 4 detectors which are, as you all know, called Atlas, CMS, LHCb, and ALICE. Of those, I'm going to concentrate on Atlas and CMS because those are the ones that really are most effective in accessing the large momentum transfer physics, which is the main focus of these lectures. So in the notes, there are illustrations of the Atlas and CMS detectors right at the beginning. I hope you all either have your computers open or have copies of these figures, because there are going to be a lot of figures in this lecture, so be aware of that. If you compare the diagrams of Atlas and CMS to the diagram of the Opal detector that I showed you in lecture 1, you'll see that the plan is really very similar, and that really follows the logic that I explained in lecture 1. You have a cylindrical detector built around the interaction point with layers of detection apparatus which will, one after another, look at the various signals that are coming out of any physics interaction. There are 2 main differences, I think, between Atlas and CMS and Opal, which are apparent in these figures. First of all, you can see that the people-sized things in these figures are much smaller. Atlas is roughly 10 stories high, a 10-story high building. CMS, whose name actually is Compact Muon Spectrometer, is only compact in relation to Atlas. It's roughly 5 stories high. I actually had the opportunity to climb on a ladder next to pieces of the CMS detector before it was installed underground in the LHC tunnel. It's really an impressive thing. You can see that CMS is built in wheels, and actually the way it was constructed was that those wheels were taken apart. Each one was lowered by crane 100 meters into the LHC tunnel, and then they were assembled back together underground. The second thing to note is that around the hadron calorimetry, you see there's extra stuff. This is especially apparent in the Atlas detector, because the Atlas detector has a solenoidal magnetic field in the center, and then a toroidal magnetic field running around the outside, given by these superconducting magnets that you see on the outside of the detector. So roughly a muon, if you look at the cross-section, will fly out in air. First of all, in the inner tracking part, it bends in one direction. Then it burrows its way through all the calorimetry. And then the idea is that in the outside, it bends in an orthogonal plane to give you 2 distinct measurements of the muon momentum, one of which is most accurate for low values, because then those muons will be ruined by their traversal of the calorimetry. And for the TeV muons that are too stiff to observe here, there's another bend outside to measure their momentum. So up to multi-TeV, one can sign muons and actually measure their momentum quite accurately. In CMS, there's a different strategy, but you see there's a lot of iron on the outside which is magnetized. It's actually the flux return. And so the muon bends one way inside and the other way outside, again to give a redundant muon measurement. The reasons muons are so important we're going to get to as we go into this discussion. Okay, so now we have these detectors about which, as I say, much more can be said, and I think you should learn much more if you're going to work in this area. Now we need to consider what the actual reactions look like. So the first kind of reaction that you might think about is the generic reaction that takes place when two high-energy protons come together. And this has to do with the proton-proton total cross-section. So the proton-proton total cross-section is actually measured at the LHC. It's not so easy to measure for reasons that we'll explain in a moment. But the value is, for the total cross-section, about 100 millibarns. And for the inelastic cross-section, about 75 millibarns. A millibarn is a large number. If you put it into the terms of the effective radius of the object that a point-like proton is hitting, the calculation is there. This number corresponds to 1.5 Fermi, 1.5 times 10 to the minus 13 centimeters. And to give units to that, the charge radius of the proton is 0.9 Fermi. So roughly, the picture you can have is that two protons, actually, these protons are boosted so much that they're Lorentz contracted, and they really look more like that, come together, and whenever they have the opportunity to touch, they liberate quarks and gluons, and pions and other materials come flying out. And so that's the basic thing that happens whenever you collide protons at the LHC or at any high-energy accelerator. Now, those interactions are mainly soft. If you think the proton is a bag that holds quarks and gluons, and in any hard contact you're going to disrupt the bag and let the constituents seep out. Those are not the reactions we're generally interested in when we want to look for new interactions in physics at very high energy. And in fact, a lot of the problem of doing LHC physics is to combat those interactions. Tomorrow we're going to talk about the Higgs boson. The Higgs boson production cross-section at 8 TeV is 20 picobarns. So we're going to go down from this number by 9 orders of magnitude. And so how you get from here to there is a big challenge. Events, as we'll talk about, can be quite complicated. And the problem is really going to be how you analyze the events. There's a top event class, which is basically just disrupting the bags. There are other event classes that are at lower levels, and every event class with a large cross-section potentially can fluctuate to look like an event class that you want to look for at much smaller cross-section. And the challenge of doing LHC physics is to understand all of these levels, and so that you know that when you measure something that occurs only in 1 in every billion proton-proton interactions, what you think your measure is actually what you're measuring. Okay. Now, the difference between these numbers is actually quite significant, and that is just a reflection of the optical theorem. Whenever you have a large inelastic cross-section, the optical theorem tells you you have a large forward cross-section, and so there's going to be an elastic scattering cross-section. And actually, there's an experiment called Totem, which is in the forward direction from the CMS detector. it basically it uses the LHC focusing magnets as an analyzing system, and then upstream measures elastically scattered protons. And I think in figure 3, what you see is some data on the total cross-section extracted from extrapolating the elastic scattering cross-section to 0 angle, and also data on the inelastic cross-section from all of these experiments. So these numbers are understood quite well, but actually they don't have much to do with the physics that we really want to talk about, except insofar as the large size of these numbers interferes with what we really want to do with the LHC. Okay, now, it's also interesting to talk about the particle production in generic inelastic collisions. And for that, I'd like to say just a little more about the quantity called rapidity that I introduced in the second lecture. So let me remind you of some formulae from the second lecture. For a particle, I wrote the momentum in the following way, as mt times cosh y pt over mt and sinh y. So I'm compressing the two transverse directions here, where mt is equal to the transverse momentum of the particle plus the mass of the particle to the 1/2. The transverse momenta of generic particles produced in these ordinary LHC collisions are of order 100 to 200 MeV. Actually, the LHC detectors make an attempt to suppress the very low transverse momentum particles. So the particles you see are very often with transverse momenta above 500 MeV. At that level, the pion mass is basically ignorable. It's very useful to take this formula and just make the approximation that we ignore the mass of the particle. Then I can write p mu as pt times, I'm going to use another symbol for it, eta 1 sinh eta. So if I have the mass equal to 0, I can represent the momentum like this, and that's quite accurate for most of the particles that are actually measured at the LHC. Well, now we can solve for eta. And so you can see from that formula that e to the eta is equal to the total momentum plus the pt divided, plus the p parallel, the p3, divided by the pt. You can also write this as p plus p parallel divided by p minus p parallel to the 1/2. And this is 1 plus cosine theta over 1 minus cosine theta to the 1/2. Well, this is pretty interesting. If we ignore the masses of particles, as we can basically always do for pions, there's a surrogate for the rapidity called eta. This quantity has the name of pseudo-rapidity, which is a very good approximation to the rapidity, and it's given only as a function of cosine theta. So this is a very convenient thing to do, which is done basically in all analyses in collider physics. You replace the polar angle by the quantity pseudo-rapidity, which is defined by this equation. To write it again, eta is equal to 1/2 the log of 1 plus cosine theta over 1 minus cosine theta. And we'll use eta instead of the polar angle to describe where particles are in the detector. This is very convenient because, as we discussed already in lecture 2, when you have a parton-parton collision, you don't know where the center of mass energy of that collision is. And so it's good to have a description which is uniform over all center of mass energies that are related by longitudinal boosts. And so this eta provides that. I'm sorry, I should have said before that figure 4 in the notes is the transverse momentum distribution of particles that are produced in LHC events at various energies. And so what you see, it's a logarithmic scale with a lot of orders of magnitude on it. So what you see is that most of the particles are produced at 100 MeV or so of transverse momentum, with a distribution that more or less falls off exponentially. And then you see a tail that grows at higher energy. And that tail is actually associated with jet production, as we're going to discuss as we proceed. This quantity eta is very important to understand, because when people quote properties of events at the LHC, typically they'll use the eta phi plane to express where things are in a detector. And I think it's important to understand what that means in real space. And so if you go to figure 5, that transformation is shown. So, for example, eta equals 0 is 90 degrees. Eta equals 1 is 40 degrees. But then, because of the logarithmic relation, as you go down in eta, things get small fast. So eta equals 4 is 2 degrees, and eta equals 5 is 0.8 degrees. So if you think about how an LHC detector is laid out, with the beam direction here, eta equals 0 is here, eta equals 1 is over here, eta equals 5 you can hardly draw where that is in relation to the beam pipe. And on the other hand, we want the detector response to be uniform in eta, because we want our description to be invariant with respect to longitudinal boosts. So typically the detection has to be very compact when you get to the forward region, and at eta equals 5 things, well, really one can't reach eta equals 5 in practice in the LHC. Well, now it's useful to make a little map of eta space. So if you ask what the rapidity is of a proton, the actual protons that come in, they're at a rapidity of 9.5. And already at a rapidity of 2 and minus 2, you're at, sorry, the number here is 15 degrees. You're at an angle something like that in the detector. And actually, if you look at where the tracking elements are in the Atlas and CMS detectors, at eta of 2.5, it's basically only in this region that you have tracking. And out to eta of 4 or something like that, you have calorimetry. And then beyond that, you're completely blind. And there's particle production over this whole region. In fact, back in the 1970s, when the big ring at CERN, the SPS, first turned on, people did fixed target experiments. And then you could look at the high rapidity region. And what people found is that in that region, there's something called the proton fragmentation region. So in those regions, the particles that you make are sensitive to what the target is. If you have a proton, if you do proton-proton collisions or pion-proton collisions, you see different leading particles in these regimes. On the other hand, in the central rapidity region, the particles that you see are more or less independent of what you're colliding together. And it's basically just the fact that there are quarks and gluons that are left behind by the big reaction. In fact, it turns out that the particle production is more or less uniform over this central region of rapidity. And I think I included here, if you just turn the page, some measurements of that from the LHC at 0.9 and at 7 TeV. You see the range, if you look at the range on those scales, it goes from minus 2.5 to 2.5. So it's really the region where you have tracking. It's also interesting that the top curves are kind of everything you can catch, and the bottom curves are particles with transverse momentum above 500 MeV. And you see that even above 500 MeV, you tend to have the particles more and more in the central region. And I think that's easy to understand for the same reason that we saw in the Drell-Yan process. If these particles are produced by hard reactions, and they have to be at high energy, it's hard for the two partons to have a large ratio. And that means that the rapidity of the center of mass of that system has to be within a few units of y equals 0. Okay, well now we have some coordinate system, and now it's interesting to try and look at events in this coordinate system. So this is often done in the following way. You draw a stripe, you let eta be the coordinate along this direction, you let phi from 0 to 2 pi be the coordinate along this direction, and then you have a plane in which you can draw the event. I've already explained to you that the ordinary soft particle production basically just sprinkles pions on this plane with a density, if you look at the plots, of about 1 pion per unit area and 1 charged pion and half a pi zero, which is to say 2 photons per unit dimensionless area on this plane. Now we want to talk about other kinds of particle production. In particular, we'd like to talk about hard scattering and jets. And that's also representable on this plane. And the usual way to do it is to use something called the Lego plot. So a way you could imagine representing an event in 3 dimensions is to take this plane, turn it on its side, and for every particle you put a little tower whose height is the transverse momentum of the particle at that place. Or if you have a coarse calorimeter or a very high density particle production, you might look at a cell of the calorimeter and plot as a tower the height of the energy deposition, or the energy deposition projected onto the transverse direction in that cell. In general, actually, it's useful to think about not energy but transverse energy, because as I've already said, there's lots of particle production. There are particles at very high rapidity. Those have large energy, but their transverse momentum is small, and they basically just come from the soft processes that we want to ignore. So very often we talk about transverse energy, ET, which is given by taking a calorimeter cell here, recording the energy in that cell, and multiplying it by sine theta associated with the angle at which that cell appears. So if I then plot the ET, calorimeter deposition, I get a picture of the event that looks something like this. In the 80s, this representation acquired the name of the Lego plot. Now, this is incredibly useful. And just to show you how useful it is, I put a couple figures here that Gustav Breumann gave me from the D0 experiment. So if you look at figure 7, what you see are an event taken by the D0 experiment at the Tevatron. And you see the tracks that come from that experiment viewed just from the side view of the detector. In figure 9, you see a second event from the D0 experiment and the set of tracks. And it's very hard from those pictures to figure out that something different is going on. But figures 8 and 10 show the Lego plot views of those pictures. And it's very important to look at the scales of these plots. In figure 8, all the little towers are only about a GeV high. So this is a soft, or so-called minimum bias event. It's an event where the proton and antiproton just smacked into each other, released some pions, and nothing really got a very large transverse momentum. But if you look at figure 10, it's a totally different story. The scale there is now 350 GeV. And what you see is a Lego plot in which basically there's an immense concentration of transverse momentum just in two places, with a height here which is, I think in that plot, 380 GeV. So this is what the event looks like when you have a quark and an antiquark that come in, have a hard scatter, exchange transverse momentum, and go out in different directions. The transverse momentum balance corresponds to the equal height of these towers, and also they should be back-to-back in phi. They needn't be back-to-back in eta, because we don't know what frame the reaction took place in. But nevertheless, you can see from this picture the events, the jets are back-to-back in phi, and it corresponds to the way these detectors view a QQ bar hard scattering event. Okay, so now I think we have some idea of how you would begin to represent the various event classes at the LHC. So now we should talk about the rates at which these event classes occur. So now I'd like you to look at figure 11, which is actually the last figure in the second lecture. It's exactly the same figure, we're just looking at it again. But now there's a little more information that I wanted to give you. So this is not a very accurate QCD calculation. It's just the most simple, stupid thing that you do with parton distributions based on the parton-parton scattering cross-sections that I told you about in lecture 2. And I told you then that there are these various classes of glue-glue, glue-quark, quark-quark reactions that you can compare as a function of PT. And what's plotted on this curve is the integrated cross-section. That is the cross-section for PT greater than the amount which is plotted. And that's a cross-section. So now you can assume a luminosity at the collider and talk about a rate. When I made this plot, I rather conservatively assumed the luminosity of 10 to the 33 per centimeter squared per second. So these are the units in which instantaneous luminosity is quoted. What you need to do is to take this and the statement that, for example, one barn is 10 to the minus 24 centimeters squared, or one picobarn is 10 to the minus 36 centimeters squared. And you multiply a cross-section in barns by the luminosity in these conventional units to get an event rate. So what I did was just to say, well, if this is the luminosity, what's the event rate? Maybe I should say that what was actually achieved at the LHC is something like 7.5 times 10 to the 33 per centimeter squared per second. So the event rates on this plot are conservative by about an order of magnitude. But nevertheless, it's interesting to look at the plot and see. 100 per second corresponds in this plot to a PT of 200 GeV. So as these protons are colliding 200 times a second, you have a very substantial two-jet event in the LHC. 1 per second, actually it would be 10 per second in fact, is at 400 GeV. So all the time at the LHC, you're not only seeing at some enormous rate the ordinary proton-proton collisions, but tens of times per second, very energetic jets that are being produced, jets that are very obviously visible in the kind of displays that I'm talking about. And once again, we're talking about picobarns or even femtobarns for new physics things that we would want to describe. So those are, well, please excuse me, that times that is 1 per 1,000 seconds. So there's all these events being produced. We have to classify them and try and understand them. One very important thing to remember also about LHC physics is that the rate of recording data is something like 200 events per second. So given the event rates that you see on this slide, even the events that really correspond to hard QQ-bar scattering can't be recorded by an LHC detector. I mean, maybe technologically you could do it, but there isn't enough magnetic tape and CDs and CD-ROMs and other things like that in the world to hold all the data. And even if you had it, you could never analyze it. And so there's a practical restriction of something like this, which turns out to be about 20 petabytes of data a year when you have a year of data taking. And 20 petabytes is like the size of the largest databases that exist in the world outside of Google and other people who make billions of dollars from this technology. So this is a real restriction. The time to decide whether an event goes into this database is roughly 1 second. And so you need a process in the LHC experiments, basically a computer farm, which takes the events which are being generated in the bunch collisions at 50 or in the next run 25 nanosecond intervals, processes that information, makes a series of decisions about whether the events are to be selected, and eventually after a second, if you haven't decided that a given event will be selected, it's then dropped and forgotten about. This system is called the trigger, and it's an essential part of any Hadron Collider experiment. If you get the trigger wrong, you take the wrong events, or if you get the trigger wrong, you might as well not have done the experiment. And so an enormous amount of effort is devoted to how this thing works and what decisions it makes. One other thing that maybe is also important to take into account is that the LHC detectors being large, the information in them is very distributed both in space and time. The speed of light is a foot per nanosecond, so in 25 nanoseconds, which is the time between the proton bunch crossings, a relativistic particle will travel 25 feet, about 8 meters. So that's basically the distance between the inside of Atlas and someplace in the Hadron Calorimeter. And so at the same time that an event is taking place in the center of Atlas, the Hadron Calorimeter is measuring properties of the previous event, and the trackers out in that muon layer are measuring properties of the muons from the event before that. And so one of the things that the experimenters have to do is to get all these signals from a given event coordinated in time so that the package of information that comes with each event is consistent and doesn't include things that overlap different proton-proton collisions. I guess as long as I'm saying all this, I should also say that the luminosity at this level is such that each proton-proton bunch crossing would produce at the total cross-section numbers that I was giving you here, not one, but about 20 to 40 proton-proton collisions. So each snapshot that you take contains many soft collisions, and then typically one hard collision of the kind that we're talking about here, and if you're lucky, one in, okay, these are coming every 25 nanoseconds, 1 in 1,000 seconds, you'll see a really interesting collision, like a Higgs boson of the kind that you might want to keep. It's a very difficult technical problem, and I think I'm going to stop here, but it's really worth your serious study how this is done. One thing that's important for theorists is that if you want to propose a search at the LHC, you'd better propose a way not only that you can find those events given an infinite amount of time, but there ought to be something in the event which would allow that event to get into the database, to be selected on this very short time scale, so that it can later be analyzed with care. Okay. Good. One more thing that I should point out about this figure 11. I didn't draw it all the way down to a momentum, a transverse momentum of 0, but you can see that it's rapidly rising on the left-hand side. And if you go down to a PT of 15 or 20, you actually saturate the total cross-section at 75 millibarns. So that means that every LHC event, in addition to having every proton-proton collision, maybe I should say, in addition to having the soft particle production, also has some jet production. Typical LHC events contain jets of 15 to 20 GeV-PT. And so if you say my criterion for selecting an event is that it has a 15 GeV-PT jet in it, you basically have to select everything. It's only when, and that also affects what happens in a given event. If you have an event that has a Higgs boson in it, it probably also has a couple 15 GeV jets whose production is completely unrelated to the Higgs boson. It just comes from a collision of some other partons in the same proton-proton collision. This and the soft particle production are called the underlying event, and part of the problem of experimentation is separating the underlying event from the kind of hard collision that you would like to really analyze. Okay, now with all that said, let's now talk about the high PT processes. So I showed you an example, both in the track view and the LEGO view, of a high PT collision from the Tevatron. The next couple figures have high PT collisions from Atlas and CMS. And you can see what they look like in these pictures. In the LEGO view, in figure 12, the LEGO view is on the left, and the track view is on the right. And maybe I should say, in this track view, all tracks with momentum less than 500 GeV are just not shown. Otherwise, the thing would just be black with tracks. So this again shows the features that I was talking about over here. In the LEGO plot, the two towers are back-to-back in phi and have roughly the same height, corresponding to transverse momentum balance in this case, probably a quark-quark scattering event. A similar event is shown in figure 13. This is from Atlas with two track views, and then down in the bottom right-hand corner, the LEGO view. And you see there a very clear, again, two-jet signature of this event. Okay. Well, now I've shown you that in pictures from hadron colliders, just like in pictures from E plus E minus colliders that I showed you on Monday, you can by eye identify that jets are being produced and that there are some hard scattering events that eject quarks and gluons. Now, however, we'd like to do better than that. We'd like to not have to go by eye and look at the pictures, but have some kind of analysis method to tell us, are there jets in the event? How many jets are there? What are their momenta? And can we be quantitative about that? Now, this is not a very easy problem, it turns out. In the lecture this morning, I told you how jets are formed. And so what we saw in the lecture this morning is that jets are a very natural consequence of collinear radiation in QCD. You start with a quark, it radiates a gluon, those gluons radiate other gluons, sometimes also quarks, and eventually what you get is a shower of approximately collinearly moving partons that at a late stage will organize themselves into hadrons, and then those hadrons are what are actually seen in detectors. The coupling constant in QCD runs, and the emission probability depends on alpha S of Q. And so in the late stages, where Q is small, the alpha S is large. And so the particle production gets very furious in the late stages of the shower. But even in the early stages of the shower, there's complexity. And what I encourage you to do is think about the case where alpha S of Q is not running, where alpha S is a constant, as would be quite accurately true for Q of order 100 or even 50 GeV. In that case, the process of building the QCD shower is scale invariant. And so what you're looking at here is actually a fractal. And as you folks know, fractals are things that require some subtlety in their description. If you take a fractal and you cut it in half, each half has exactly the same structure as the thing you started with. And so, given that this is true of jets, we have to be somewhat careful about how we define jets, and we should find a definition that's good both for experimenters and for theorists, so that we can talk in a common language. So let's talk a little about that. Now, I'd like to go back to E plus E minus, where the situation is a little easier. So in E plus E minus annihilation, particle production is central. We can imagine that in a detector like the Opal detector, we can pretty much see all of the particle production. And we can describe the various tracks, photons, etc., as associated with different angles in this detector. And we can associate four vectors, pi, mu, with all of those objects. Now the question that I'd like to ask is, are there jets in this event? How many jets, and what are the momenta of the jets? So the idea that people got when they studied these events is that you need a method for clustering the various momenta that you see, and then at some stage you will define the clusters to be jets. So the one very simple way to do that is something called the JADE algorithm. So this was developed in the experiment called JADE at DAISY in the 1980s. Actually, there's one of the big experts on QCD, a fellow named Siggy Betke, when he was at the beginning of his career, played a big role in the development of this algorithm. Let's define Yij to be Pi plus Pj squared divided by the total center of mass energy in the reaction. And we can define this quantity for every object that appears in the event. The momenta, in the ideal case, at least summing to the total energy which is liberated in the reaction. Another way to write this is that this is Mij squared over S, the m squared compared to the total S in the event. And we can define this quantity for any pair of particles, let's say this one and that one, that we detect in the detector. Now what we'd like to do are to cluster these particles into things that would naturally be related by the QCD jet evolution that I've shown over here. And so what's suggested is that we go through an algorithm which is the following. We start from our collection of Pi. We then combine the particles I and j with the minimum value of Yij into one particle. So where there were two particles before, we add the four vectors, and now we have one particle. And now we go back to here, and we iterate. And we leave the loop when all Yij are greater than some conventional number called Y cut. Then the particles that we have at this stage are defined to be the jets. So we've clustered the original particles into a finite number of clusters. Those have associated form momenta. We define those to be the jets, and now we're done. It's a natural way of doing things. It associates particles which have small invariant mass, and two particles with small invariant mass are very likely to have been created by the late stages of a shower that looks like this. Actually, we can also imagine that we do a QCD calculation where we, for example, have E plus E minus and we produce, let's say, 5 partons. And then in that QCD calculation, we can try and associate the partons using the same algorithm. And then you can comparison. Do you get the same number of jets from the QCD calculation at a given energy as you do from experiment? So in the next figure, which is figure 14, there's a comparison. And this figure is interesting for 2 different reasons. First of all, it actually works. If you generate particles in a QCD shower by basically a computer program that implements the Altarelli-Parisi evolution of a single quark, you then easily generate, using the collinear approximation, many, many quarks and gluons in an event. If you then cluster those quarks and gluons using the Jade algorithm, you can predict the number of jets as a function of y-cut, and it's actually in very good agreement with experiment. So the QCD picture works, and we actually test it by looking at this jet number that we observe in experiment. But you also see this fractal property that I talked about a moment ago. The number of jets in an event is a convention. It depends on the value of y-cut. And so if you take a large value, you'll basically cluster all of the tracks into 2 jets, which are then almost by definition back to back. If you take a small value of y-cut, you're somehow resolving the tracks in the event to a greater extent. You're not doing so much combination, and you have a much larger number of jets in the event. And in the figure you see that if you take a y-cut, which is 1/10, that basically all the events are 2-jet events. At a y-cut of 10 to the minus 2, there's a very substantial population of 3-jet events, which basically have the following origin. You start from a QQ bar, you then radiate a gluon, and this one is at a sufficiently high transverse momentum that it's not combined with these 2 when you do the jet algorithm. If you let y-cut get really small, you resolve the event more effectively, and so even the more collinear gluons are not combined into jets. And so then you might have 5 jets in the event, or 6 jets, as you see on the left-hand side of this curve. So this really emphasizes several things about jets. That jets are conventionally defined objects. They're defined by some definition that we impose from outside. If we want to do comparisons between theory and experiment, we need to specify an algorithm by which we cluster particles or energy depositions into jets. And we need to use the same definition in the theory and the experimental determination of the number of jets and their properties. And we can have different levels of resolution at which an event might have more or fewer jets. So all these things are very important to take into account when you think about how to use jets in order to analyze events in high energy collisions. Okay, well, now we go from E plus E minus to proton-proton. And now you see that there's some problem that we have to confront, which is that in the E plus E minus setting, we're basically measuring all the tracks and all the energy deposition. But in the proton-proton setting, we're only measuring what's in the central region. And there are things that are forward. There's a lot of energy going forward that's totally invisible to our detector. So you need a different strategy. And the strategy that people have evolved are basically based on this eta phi plane that I told you about before. So let's go back to eta and phi. And of course we have the soft particle production, one per unit area over this plane. And then we have jets, which intuitively are clusters of particles with very high transverse momentum at specific places in this plane. And so roughly what you would like to do is to figure out where there's a high particle density, or better, a high density of transverse momentum, kind of draw a circle around those regions, and consider those things to be the jets. And now let's talk about how to do this in a more organized fashion. So first of all, let me define a distance between particles, or actually, typically at the LHC, this is done with calorimetry. So maybe a better way to draw the picture would be to think about the calorimeter barrel as being divided into cells like that. And each cell has some energy deposition. And then we have some signals which correspond to the eta, the phi, and the pt that we might find in those cells that register some energy above background. Then we can define delta Rij as the distance on the eta phi plane between two depositions. So eta I minus eta j squared plus phi I minus phi j squared to the 1/2. Remember that eta and phi are both dimensionless variables, and they're both basically angles. Phi in physical space and eta in the extended space that you have with the Lorentz group. Now, once we have this distance measure, this separation in the eta phi plane, we can define a distance measure between two energy depositions. So one defines dij is equal to the delta Rij divided by r, some input number. And then in front of this, people often put the minimum of the pti and ptj to the power 2 alpha. So let me write that. And then there's one more distance that we need, dib, the distance to the beam, you might say, which is the pti to the 2 alpha. So now a jet algorithm would go like this. We pick a value of alpha and we pick a value of r. So that gives us some flexibility in what resolution we take and how we associate things as a function of momentum. We then go through all the various energy depositions in the calorimeter, and we look for those pairs which have the minimum value of this distance, and we add the 4 vectors. Then go back and iterate, and what will happen at some stage is that the minimum will be the dib, and so a given 4 vector will drop out of the program because it will be associated with the beam. And so as you iterate, you can either combine I and j or associate with the beam. And at the end of the process, you have a set of final depositions which are associated with the beam, and those are what you define to be the jets. So let's ignore the momentum dependence for a moment and just think about how this works. So this would be 1. This is delta Rij over r. So in that case, this is the case now alpha equals 0. What you would roughly do is that you'd put together energy depositions that are closer than your canonical distance r. And when everything is separated by a distance greater than r, everything gets associated with the beam, and those are the jets. This is very close to what I was doing here. This algorithm where you draw circles is called the cone algorithm. It turns out to be a very problematical algorithm because very often the best circles will overlap one another. And then you have to talk about how you cut the circles apart. But this is the algorithm that basically people used at the Tevatron. For the LHC, it was thought to do it better this way with alpha equals 0. And this is an algorithm called the Cambridge-Aachen algorithm. If you want to imitate what the E plus E minus folks did, you can set alpha equals 1. So there, basically, there's a higher probability to associate soft particles, things with low PT, with some jet, although it may not be the jet that's closest. And this is called the KT algorithm. And actually, eventually, some really clever people, Gavin Salam, Soye, and Cacciari, whose name I should probably spell correctly, proposed putting alpha equals -1. And this is called anti-KT. And for that algorithm, what happens is that if you have a somewhat large value of PT, it sucks up all the energy depositions around it up to a cone size of about R. And so then you get actually very regular cones, much more regular than either the cone algorithm or the Cambridge-Aachen algorithm produces. Now, associated with this, there's a subtlety that I forgot to tell you about, and so we have to go back a little and talk about that. In describing these algorithms, I haven't paid much attention to the theory side, but the theory side is actually very important, because ultimately you'd like to have a jet definition that's useful for theorists as well as experimenters. On the theory side, there's a natural problem with jet algorithms, because remember that when we were discussing QCD, we decided that the radiation of a soft gluon or a collinear splitting, so if you have energy going to 0, or if you have the PT going to 0 in a collinear splitting, and you actually calculate the diagram, you get infinity. You get a divergent propagator. So it becomes very difficult for a theorist to compute the number of jets if you're sensitive to whether either of these processes occur. And so this gives rise to a notion of soft and collinear safety of an algorithm. So an algorithm is soft and collinear safe if you get the same jets in the end, whether or not you radiate a soft gluon or whether you have a collinear splitting. This is a property of the Jade algorithm, because the Jade algorithm basically looks at invariant mass, and all of these basically lead to systems with 0 invariant mass. So if I make this splitting in the situation of E plus E minus, and then I run the Jade algorithm, the first particles or energy depositions that I would associate are the ones that result from a collinear splitting or a soft emission. And then I get back to what I had before the emission. So basically, if you compute with or without these particular kinds of particle splittings, you get the same jets in the end. It turns out that all of the algorithms that I've described here also have this property of soft and collinear safety. And the surprising thing these people pointed out is that even alpha equals -1, the algorithm has the property that if you have a soft and collinear splitting, it doesn't make any difference to the final set of jets that you get after you run the jet algorithm. So it turns out that this is just an extremely convenient algorithm, which is used as the canonical jet definition by the LHC experiments Atlas and CMS. Just to give some kind of tactile idea of this, please look at figure 15, which is from some actually really very useful set of lecture notes by Gavin Salam on jet physics. So in this figure, he generated, using the Herwig Monte Carlo, a complex LHC event. And then he applied various jet algorithms to it and asked what jets appear. And the colors code the different jets. And you can see that actually there are different associations, and the jets have different sizes and shapes depending on the details of the algorithm. So once again, it just emphasizes that jets are defined by convention. You have to get your conventions straight. You have to make sure that the conventions are soft and collinear safe, so that using theory, you can make a prediction about the number of jets and their energy distribution. And then, obviously, it has to be convenient and computable if the experimenters are going to use it. The Cambridge-Aachen and the KT algorithms are used for some purposes in the LHC experiments. In particular, I probably am not going to have a lot of time in these lectures to talk about boosted particles. But these algorithms are much more closely related to the actual path by which QCD turns a quark into a jet. And so if you want to think about reversing that process, trying to look inside jets, these algorithms are much more convenient than this one. But this one, which produces very regular kind of cone-like or circular jets, is kind of the workhorse algorithm for the LHC experiments. And we're going to see a lot of anti-KT jets when we go into detail about LHC searches in Lecture 7 of this series. Okay. Well, now I've told you what a jet is. For the most part, when we talk about jets in the rest of this lecture, we're talking about anti-KT jets. And actually, there's an odd thing that when you try and decide the optimal size of a jet, which I now think of as a cone, which is a circle on this plane, there are two effects you have to consider. First of all is that if you have a QCD object inside, it can radiate a gluon or a quark outside the cone. And you'd like to minimize that. So you'd like to have a jet definition for which it's relatively rare to radiate outside the cone. On the other hand, you have all this soft production that go into the cone. And so you'd like to balance the radiation out with these soft particles coming in. And so before the LHC started, people in ATLAS and CMS thought very hard about this. And in ATLAS, they came to the conclusion that the right cone size was R equals 0.4. And in CMS, they came to the conclusion that the right cone size was R equals 0.5. And don't ask me why, but when you see ATLAS plots, typically you have R equals 0.4 anti-KT jets. And at CMS, you have R equals 0.5 anti-KT jets. Okay. Okay, that means that the jet rates calculated by those two experiments are going to be different. And they're different because the definitions are different. And then in each case, you have to compare to an appropriate QCD calculation to see whether you're in agreement with experiment. Okay. No one said that physics of large collaborations is simple. Okay, now please look at figure 16. So when we have jets of finite size, we do have some rare events in which you do radiate hard gluons outside the jet. So if I have a quark-quark scattering reaction, there are lots of places in this reaction from which I can radiate extra gluons. Those gluons are typically collinear, and so they're sucked up into the jets that are being produced, but with some probability they can be radiated at large angle. And that probability is not so hard to estimate. If we have, for example, gluon-gluon scattering, there's a 3, there's an alpha S over pi. This number is about 1/10. And you can think that with a probability of about 1/10, you should have, in any QCD situation, an extra hard jet at large angles to the jets that you've already found in a given reaction. So in figure 16, I show a plot from ATLAS, which gives the number of R equals 0.4 anti-KT jets that you find in their sample of LHC hard scattering reactions. And roughly the steps, they're uniform on a log scale, are about a factor of 10, as this kind of estimate would give you. And, well, remember, the top layer here are things that are just happening all the time, you know, hundreds per second. And so as you go down, you have high rates for processes that become very complex. And so when you go down by 5 orders of magnitude, you find 6 jet events, which again are a commonplace at the LHC. And just to demonstrate that, in figure 17, I show you an event display of a 6 jet event, which was actually seen in the first year of LHC running. Just after they turned on, they picked up that event. And its rate is perfectly consistent with the rates that are shown in this figure. By the way, the figure 16 has comparisons to various QCD Monte Carlo programs, so the programs that simulate the Altairelli-Parisi evolution of showers. And those programs do, in fact, account in a reasonable way for the number of jets that you see. One can also do that more cleverly by doing a real QCD calculation of, for example, 2 quarks to 6 quarks or 6 quarks and gluons. And some of the programs, in particularly the program called Sherpa, has very efficient techniques for generating those high multiplicity QCD processes. Okay. Now, at this point, I've convinced you that doing LHC physics is really hard. And so, despite the fact that it's really hard, what we want to do is to use the LHC as an engine to discover new processes beyond the standard model. So the first priority, as I hope I've now sufficiently emphasized to you, is to get out from under the influence of QCD, to find classes of events that are very rare in QCD, where we can really look for other kinds of processes that appear. And so basically there are 2 ways to do that. One way is to go to high energy, of course the 0th way is to go to high energy, large transverse momentum, and large complexity. But I've just told you that really doesn't do you much good. So now you need some other tools. And the 2 tools that are most common are missing ET and leptons. So we need to talk a little about both of these things. I've defined ET as calorimeter energy projected onto the transverse direction. Whenever we have quarks and gluons, the event naturally has transverse momentum balance. You produce as much momentum in quarks and gluons going one way as another. So if you have a new physics signature, or even an old physics signature, that has invisible particles in it, those particles won't show up in the detector, and so they'll signal that you're in an event class which is not in QCD. And so missing ET is something which is very important in order to indicate those event classes. Now, there's a lot to be said about missing ET, but the simplest thing to say about it is that it's very hard to measure. The easiest way to have missing ET in your event sample is when the detector over here is working and the detector over here is not working. Then obviously you would see an imbalance in transverse momentum. And so the experimenters actually work very hard to mitigate this particular effect. There are always noisy cells in a calorimeter. You have to turn them off or correct their response. You have to look at where, for example, the cables are in the detector, so you're not having a full calorimeter response in those particular regions. You have to worry about what's going on in the forward direction, etc. After years of effort, Atlas and CMS actually do extremely well at measuring missed ET. And just as an illustration of that, in figure 18, that comes from an Atlas performance paper, and it shows the resolution in missing ET. And if you look at the numbers, it's really pretty spectacular. A resolution of, for example, of order 10 GeV in missing ET for an event with 400 GeV of total ET. The dependence that the resolution delta ET goes like the square root of ET is again an illustration that this is some kind of statistical or sampling effect. So there's a certain point at which the detector just fluctuates and there's nothing you can do about that. But what they do is really, it's just amazing how well they do. I think if you talk to experimenters before this program, they would never have predicted that they would get to this level. So it turns out that ET is actually a pretty useful way to distinguish reactions that are not completely from QCD. The other way is to look for leptons, because leptons, in particular leptons that are not in jets, that don't result from like B quark decay or charm quark decay, are characteristic of producing objects through the electroweak interaction, which is distinct from QCD. Now, of course, the simplest way to get leptons is by the Drell-Yan process, where you have a W that goes to L nu, or a Z that goes to L plus L minus. Maybe I shall also just remind you that the Z goes to nu bar, and this is a 20% branching ratio. So 20% of the produced Z's have missing ET, and this is something more like 6% if you include electrons and muons. Oh, sorry, please excuse me, 4%. If you include electrons and muons, that's the number, 4.6%. If you include electrons and muons have lepton pairs in them. But nevertheless, looking for things that are in these classes gets you out of QCD and gets you some handle on what can lie beyond. Another thing that you might add to this list are the presence of heavy quarks. But frankly, that also doesn't really do you much good. The heavy quark production cross-section at the LHC is very large because you can just have glue, for which there are, millions of gluons in the proton, as I've already emphasized to you, producing BB bar. And the cross-section for this process is something like a millibarn. And so even if you insist that the B's are in jets, the rates are very high. This is something that's going to come back and burn us in the discussion of the Higgs boson that I'll talk about tomorrow. But sometimes the presence of B's in connection with some of these other signatures can again get you out from the region where you're dominated by QCD. Okay, now please look at figure 19. So now we come to this very important stage where we can talk about all the various reactions that appear at the LHC. And this is a very nice figure produced by in the US SNOMAS study last year, which are the predictions of a whole variety of cross-sections, the QCD predictions for those cross-sections. So you see up at the top, this is in nanobarns. So 10 to the 8th nanobarns is 100 millibarns. Up at the top you see the total cross-section. Then you see BB bar and jet cross-sections at a very high level. And then it's a log scale with many decades. And as you go down, the next thing you encounter are the Drell-Yan cross-sections. Then down from those, the next thing you encounter are the top cross-sections and Higgs cross-sections. So I guess what we ought to do now is discuss these cross-sections one after another. So let's do that. So the Drell-Yan cross-sections you see, let's see what I picked up for the canonical numbers. The Drell-Yan cross-sections are at the kind of 100 nanobarn level. The top quark cross-section is at the 100 picobarn level, although that rises to close to a nanobarn when you go to the 14 TeV or 13 TeV LHC. And then the typical event rates for new particles that I'm going to talk about on Monday, that's at the picobarn or fractions of picobarn level. So even associated with these kinds of processes, there are things that you have to worry about in relation to how you search for new physics. Okay. These Drell-Yan cross-sections are very well understood. I think there's, in figure 20, you see the measurements at the LHC and at earlier colliders compared to the precision theory. The program that these that the experimental numbers are compared to is a next to leading order calculation of the cross-section. You see the agreement is really good, so these production rates are very well understood in QCD. Maybe the next figure is a little more interesting. Oh, and sorry, and just to convince you that these things are real, I included 2 event displays of W and Z Drell-Yan production from CMS and Atlas. So let's now go on to figure 23. So just as we have in a quark-quark collision the possibility of radiating gluons and quarks in various ways from this collision, making complex multi-jet events, something that you have to worry about when you have leptonic signatures is that the same thing can happen in that case. So you could, for example, have a WL nu subprocess with QQ bar annihilation, but then it's very hard gluon radiation from the initial state. And once again, as we saw in the case of multi-jet production, with about a factor of 10 step, you can get extra jets that appear in those events. So in figure 23, what you see is the measurement of W to mu nu plus jets at various jet numbers. And once again, you see this structure, which I like to call a staircase, where kind of uniformly on a log scale, you step down by an amount of order 1/10 from the jet rates for every process. Now actually there's something interesting about this curve, because what you see is the data, and then the data is compared to some theoretical prediction, and in the various colors on this curve you see the things that make up that theoretical prediction. Now when you look at a log plot, when there's an area on top, that's basically everything. And then the other components are very small components until they begin to dominate. But you can see that when you get to jet numbers of 4 and 5, the green stuff is dominating. And the green stuff is actually top quark production. TT bar, the top quark decays to BW and B bar W minus. And then this process can now give you a lepton and a neutrino. The W can also turn into jets. And so ultimately at the highest jet numbers, it turns out to be the top quark cross-section, which dominates what you would consider to be the W plus jet production. And this is a feature of top, which is actually very important to realize at the LHC, because top is, on the one hand, a very large cross-section from the point of view of the standard model, but on the other hand, a very annoying cross-section from the point of view of going beyond the standard model. So now maybe we should talk a little about that. I think in the next slide, 24, there's the comparable distribution for events that are consistent with Z to mu plus mu minus plus jets. And there, actually, the top is the green. And even when you get to 6 or 7 jets, if you select 2 leptons that are consistent with a Z, top has a significant effect there. So now we really need to talk about top. So maybe the first place to talk about top is to look at the top cross-section. And so in figure 25, what you have are the measurements of the top cross-section on the right at the LHC, and then the little star way on the left is the measurement of the top quark production cross-section in PP bar collisions at the Tevatron. Actually, the Tevatron and the LHC are not so far apart. The LHC at 7 TeV, or 8 TeV, is only 4 times the energy of the Tevatron. And there's certainly an advantage in producing some new thing if you use proton-antiproton versus proton-proton collisions. That's the blue curve versus the green curve among the theoretical predictions. Nevertheless, the top cross-section at the LHC is larger by a factor of 30. And it's a really surprisingly large number. Particle theorists tend to consider this in a very blasé way because they say, well, it just agrees with the prediction of QCD. But nevertheless, as students, you should ask yourself, well, that's really weird. Why does that happen? And so I'd like to just talk a little about that. So top quark pair production in a hadron collider, there are two mechanisms. One has to do with a QQ bar initial state, where you annihilate a quark and an antiquark to a gluon, and this produces TT bar. The other comes from a gluon-gluon initial state. And there are three diagrams, which let me just draw them here. Okay. Now, these diagrams are different in some important ways. First of all, the QQ bar process is pure S-channel exchange, whereas the glue-glue process is dominated by T-channel exchange. Whenever you have T-channel exchange, there's some large integral of d cosine theta over 1 minus cosine theta or something like that. So you get a numerically larger answer. Also, when you have gluons, you have the color charges here. And so there are just larger color charges in these diagrams than those you see over here. And so numerically, this cross-section tends to be larger by about a factor of 5. But that's one effect, but the other effect has to do with parton distributions. The parton distributions for valence quarks, as we've said, are peaked around values of 1/3, and the parton distributions for gluons, although they're much, much larger, tend to be peaked at smaller values of the longitudinal fraction x. So at the tevatron, at 2 TeV, in order to make a top quark pair, you had to have partons that were more or less in this region. And there just weren't enough gluons there. The particle production was entirely dominated by the valence quarks against the valence antiquarks in this proton-antiproton collision. On the other hand, with a step of a factor of 4 in energy, you could now make top quarks from the gluons here. And there are just a lot more gluons than there are valence objects in a proton. So the combination of those two factors, if you evaluate it carefully, gives you this step, this, frankly for me, quite amazing step of a factor of 30. It puts the top quark cross-section as one of the most important non-ordinary QCD cross-sections at the LHC. As I said, at 14 TeV, it's very close to a nanobarn. And so it becomes comparable to Drell-Yan and other processes you might want to look at. By the way, the agreement between theory and experiment is really spectacular. In the past year, there was just an unbelievably difficult QCD calculation of the total cross-section done by Chacon and Mitov. Really the state of the art in the difficulty of quantum field theory calculations. And as you see, it is in beautiful agreement with the data. Okay. To show you what these events look like, please look at figure 26. So there you see an event display of a candidate event for top quark production. And now maybe I just should talk a little about that. So the top quark has a mass which is something like 172 GeV. It's sufficiently large that the top quark can decay to an on-shell W and a bottom quark. So whereas for all the other quarks, the weak interaction is an off-shell process. For example, in beta decay, you have a virtual W that then turns into leptons or quarks. For the top quark, the W is on-shell. And this has some interesting consequences, both for the angular distributions in this decay and also theoretically, that I'm going to take up in the next lecture. But just to tell the simple story here, the W now decays to lepton and neutrino also tau neutrino, and then UD bar and CS bar. So it has a multiplicity of decay modes. And if you also have an anti-top in the event, oh, sorry, this now has the same multiplicity of decay modes. What that means is that when you analyze top events, there are three different classes, which are rather different from one another. The cases where you have hadrons on both sides, the so-called semi-leptonic events where you have leptons on one side and hadrons on the other side, and the dilepton events where you have leptonic decays on both sides. If you think of this in terms of trying to understand the physics of the top quark, it's very interesting, because these different event classes have different benefits and difficulties in terms of getting at the various aspects of top decay. So for example, in tomorrow's lecture, I'm going to talk about a top quark measurement where the use of the semi-leptonic decay channel is very useful. On the other hand, if you think about the top quark with this 1 nanobar in cross-section as a background to new physics, you have to worry about all of these things. The dilepton decay has 2 leptons, missing energy, and jets, and they're even B-tag jets. So it produces a certain kind of background. The single leptonic decay produces, as we've talked about already, the dominant source at large jet number of things with leptons, missing energy, and quarks. And of course, the totally hadronic decay gives you another source of background for these very high complexity events you might use to look for very heavy particles that decay only to things that interact with QCD. So it's really something that you want to look at here. I guess that's, I guess just to impress you about how visible top quarks are, please look at figure 27. So this is a very beautiful paper from CMS, which attempts to measure the top quark mass in a very direct fashion. And so what these people did was they looked for 6 jet events with 2 B tags. So there are events that are consistent with TT bar production with the fully hadronic channel. They then looked in these events to see whether there were 2 jets that had the mass of the W. And so you did a further selection, and the selection was made rather tight. Well, it turned out that there is a selection which still leads to a very large event sample, which, as you see from this figure, is virtually background free. And then you try and associate, for example, 3-jet systems on one side of the event and plot the 3-jet invariant mass, and you get a beautiful mass peak, which then can be used to rather accurately measure the mass of the top quark, the parent of these 3 jets. So it's kind of amazing how well you can do, on the one hand, studying the top quark with this large sample of events that's rather distinct from the rest of QCD. On the other hand, as we'll see, this is going to be a big annoyance when I talk on Monday. Now, there's one more important class of events that I shouldn't stop without mentioning, the single top events. Single top is an electroweak process, but it only has 1 top quark in it, so therefore it can have a rather large cross-section. And in fact, the largest single top process has a cross-section comparable to TT bar, and it's also something that's important to think about. There are 2 different mechanisms for single top. One of them is essentially fusion of a W and a B. So the B can be produced either by gluon splitting, or if you like, by soft gluon splitting, which means the B is just a parton in the proton. The W, it's a little harder, so usually we think of that as being radiated by some quark. For example, a U quark that turns into a D quark. And I guess really the W can be thought of being in the T channel, so this is called the T channel mechanism. Another way to produce single top is by a QQ bar annihilation to a W plus, that this is called the S-channel process. So typically this is the big one. It's asymmetric between T and T bar for the same reasons that the W distributions are asymmetric, as I talked about in Tuesday's lecture. And it has a large cross-section, again, hundreds of picobarns on this side. So it's something that you really have to think about in the totality of LHC events. Okay, well now we've gone through the various difficulties of doing experimentation at the LHC, the various event classes, the various, if you think about it a little more carefully, theoretical problems which must be overcome in discussing these events. So now we're getting to be in good shape with collider physics. And so now we can begin to talk about some of the more interesting topics that are the questions that are brought up by these kinds of analyses. So in tomorrow's lecture, I'm going to talk about the properties of W's and Z's at high energy and tell you some things about those that I hope you will find very interesting. In Friday's lecture, we'll talk about the Higgs boson, and in Monday's lecture, we'll talk about how to search for new particles. So, see you then. Okay, you have the microphone. Any questions? Please.
Is there a way to distinguish between jets in an event that originate from quarks or gluons?
Oh, there's something about that in the notes which I didn't actually talk about, but this is a very interesting question. You would really like to, on an event-by-event basis, tell whether a jet came from a quark or a gluon. And it's a difficult thing to do. But in a statistical sample, there are ways to understand. So there's an equation which is in the notes. That, remember, if I have a jet, the structure of the jet is determined by basically the first splitting. The first splitting tells you how wide it is, and it also, well, roughly, when you have a gluon, you then tend to make more gluons. And the multiplicity in jets is always dominated by a multi-gluon cascade. So if I start with a gluon, I'm much further along toward creating many particles than if I start with a quark. And so roughly the multiplicity, if I start from a quark, with respect to the multiplicity, if I start from a gluon, the average multiplicity is something like the t squared over t squared, which determines the strength of these interactions. And this number is, please excuse me, 4/3 divided by 3, or 4/9. So on the average, you would say a quark jet has half the multiplicity of a gluon jet. So this is basically the way you try and distinguish. If a jet has higher multiplicity, if it has more subcomponents, if it has a larger transverse momentum, which corresponds again to an earlier splitting here, it's more probably a gluon jet. If it has a smaller number of particles than the average, a smaller transverse momentum, it's more probably a quark jet. But those two distributions overlap substantially. And so it's very hard to do this on an event-by-event basis. You can only really do it by comparing a sample of events over here to another sample of events over there. There's a very beautiful plot that I debated whether to put into this, and in the end I didn't. But let me draw it for you, because it's I can get you the reference afterward if you'd like it. This analysis was first done at the Tevatron and then repeated by Atlas at the LHC. So if you look at PT, you can look at a quantity called 1 minus psi of 0.3. So roughly, you take a cone where the cone size at the LHC is 0.7. sorry, at the Tevatron they used cone sizes of 0.7. And then you draw a cone inside it of 0.3. And what you ask is, what fraction of the PT of the jet is outside the inner cone but inside the outer cone? So this is a measure of the breadth of the jet. Then you look at that as a function of PT. Now, remember I told you that gluon jets are broader because the initial splitting occurs earlier because the QCD charge is higher. The quark jets are narrower. So if you then ask Pythia what these numbers should be for quark and gluon jets, you'll find some curve like this for quark jets and some curve that's up here somewhere for gluon jets. And if you ask what the data says, the data, the data likes this dependence. And this is exactly what you would like. Because remember that diagram that I showed you. For small PT, you're dominated by glue-glue reactions. For large PT, you're dominated by the reactions of the hardest partons, which are the valence partons. And so you should cross over from this curve to this curve as a function of PT. And indeed, that's what the data says happens. So there is discriminating power. It would be nice if it were easier to use, but at least it's there.
Thank you.
Please. Oh, wait for the microphone.
There's something you haven't explained that's probably worth mentioning, is why the protons at the LHC have rapidity 9.5 and not
sorry?
infinity. Is it better like this?
Why is the rapidity of the proton 9.5?
Yes, it's probably worth mentioning, I guess.
Oh, I'm sorry. It's please excuse me. E equals m times the cosh of y. Okay. So if you put the proton mass here, you put 14 TeV here. This number is 9.5, if I computed it right. It's just that. Okay. Any other questions? Okay, well, think about this. If you don't have any other questions, you're in trouble, because all this material we talked about in this lecture, it's very, very subtle. And so as you think about it, I'm sure that questions will arise, and please come and ask me. Okay, thank you.